Sarah Zerbes will give now the first talk of this morning, which is the second talk in their series of lectures on higher Hida theory and p-adic functions.
Thank you very much, Adrian. So I'd like to thank the organizers for inviting David and me to give the lectures here. And before I start, I would also like to say something to Henri. So Henri, 10 years ago, you suggested to David and me that it should be possible to construct new Euler systems. And you very generously shared all your ideas with us. And in some sense, all of our work since then has followed from these very first computation that we did on valence and Flach elements, following your suggestion. And in some sense, today's results are a generalization, or they are inspired by your beautiful work with Massimo and Victor in the valence and Flach case. So I would like to dedicate this talk to you and to thank you for all your guidance and support during the last 10 years. Okay, so the topic of my talk is to relate the GSP4 Euler system for the spin representation attached to genus to Siegel modular forms to the p-adic function that David constructed yesterday. So let me just briefly recall the setup. So we let pi be a cuspidal automorphic representation of the group GSP4. And I call the weights R1 greater or equal to R2 greater or equal to 0. And I let alpha, beta, gamma, and delta be the roots of the Hecke polynomial ordered by p-adic valuation. So, sorry, I can't write very fast with this pen, so I switch over. So I assume that pi is Klingen ordinary, which means that the p-adic valuation of alpha beta is equal to R2 plus 1. And I define the polynomial p of t to be 1 minus t over alpha, what? 9. T over alpha times 1 minus t over beta. Okay, and I write v pi for the spin Galois representation. So attached to pi. So that's a 4-dimensional Galois representation. So yesterday, David constructed a p-adic function, so LP of pi, and this LP of pi has the following property, that LP of pi evaluated at J is equal to L spin of pi evaluated at J for the critical values. So which is just the interval from 0 to R1 minus R2. Right, so today, we want to give a geometric interpretation for the values LP pi of J, where J is in the geometric range, which is the interval from -1 minus R2 to -1. Right, so let me first recall the construction of a motivic cohomology class. So this is joint work, or this was joint work with David and Chris Skinner. And it was inspired by work of Francesco Lemma. Okay, so we let as before, so G is GSP4. So associated to that, we have the Shimura variety with Klingon level structure at P. And I will write XG Klingon for the toroidal compactification. Right, so then we have the subgroup H. So this is GL2 times GL2, where we take the fiber product over GL1. So this gives rise to a Shimura variety, which David denoted YH delta. So this is very special level structure at P. And we have an embedding iota delta of YH delta into YG Klingon. Okay, so now we let V be a local system so which is associated to the algebraic representation, so which we call V of R1, R2, R1 plus R2 of G. Did David define this representation? Well, okay, I mean, let me just sort of say, I mean, it is attached to the weight. So if we have an element of the torus as x, sy, sy, as y to the minus 1, as x to the minus 1. So this is sent to x to the r1, y to the r2, s to the r1 plus r2. And I say here sort of some local system, I mean, well, in the cohomology theories, I mean, that I'm going to discuss. So I let Q be an integer between 0 and R2, and I define the pair T1 and T2 to be R1 minus Q and R2 minus Q. And I then consider the following local system on YH. So it is attached to sim T1 times sim T2, I mean, of the standard representation for GL2. So we then get a push forward map. So from the H2 motivic of YH delta with coefficients in the dual of W twist 2, so into the H4 motivic of YG Klingon with coefficients in V dual 3 minus Q. Right, so the idea is now to take a suitable element in this motivic cohomology group and to consider its push forward under this map. So we have in here, which I will call ICE T1, T2 motivic. So this is just the exterior cup product of two motivic GL2 Eisenstein classes, which are generalizations of Siegel units. Right, so and we define Z to be the image under this push forward map. Right, we now remember the formalism of Abel-Jacobi maps. So from the H4 motivic, we have an étale regulator map into étale cohomology. So this here is our étale. So from here, we have a projection map into Galois cohomology of V pi dual minus Q. And we can then apply the Bloch Kato logarithm to end up in the dual of the fill 1 plus Q of Diderot of V pi, of V pi all dual. And the composition of these maps is called the Étale-Abel-Jacobi map. Let me just make a little remark here. So in our Euler system paper, where we do the construction of these Syntomic homology classes, we actually work at spherical level and we consider the diagonal embedding. I mean, it is not very hard to relate this class Z to the bottom class of the Euler system constructed at spherical level. But it is this class that we can relate to the p-adic function. Right, so what is now the idea? The idea is to evaluate the image of the class Z under the Étale-Abel-Jacobi map, so against suitable elements of Phil 1 plus Q of d de Rham v pi. Right, so where do these suitable elements come from? They come from this class in coherent cohomology that David mentioned yesterday. So we let eta be the element in the H2 of xg Klingen, which is isomorphic to the Phil 1 of d de Rham of v pi over Phil R2 plus 2 of d de Rham v pi, so as in David's talk. Right, so then by weak admissibility, so there exists a unique lift which I will call eta de Rham, of eta to the intersection of the kernel of P of phi and the Phil 1 of d de Rham of v pi. Right. And then by the way that the filtration, the Hodge filtration on d de Rham works, we can regard eta de Rham as an element, which I will call eta de Rham Q, which lives in the Phil 1 plus Q of d de Rham of v pi. So for Q in the range between 0 and R2. Right, so we now have the following theorem. So this is joined with David, that if we pair the image of this class Z against the eta de Rham Q, then this is up to an explicit non-zero factor, a non-critical value of the p-adic function. Namely, it is the value at -1 minus R2 plus Q, which is a non-critical value. Right, so what I want to do in this talk is to describe an outline of how we prove this result. So, I mean, this is going to be rather technical, but I'm trying to be as clear as possible to explain the different steps of the proof, and in particular, to explain what is just the standard approach and what is genuinely new. So the next section is the reduction to Syntomic homology. Well, I first want to make some remarks. So the first one is that I will ignore all issues regarding the cuspidal boundary. Okay, so I will ignore all issues regarding the cuspidal boundary. I mean, it turns out that there are some rather delicate issues. I will hint at some of them later, but I'm not going to explain, I mean, how we deal with them, and I'm not going to keep track of that. And the second remark is, so in our paper, we use at least 5 different versions of Syntomic homology. I'm going to blur the distinctions between these different theories. So I will ignore the differences between different versions of Syntomic homology. I mean, in fact, if you haven't met Syntomic homology before, so for us, so Syntomic homology so this is going to be a mapping fiber. So it's built as a mapping fiber. So how did I put this? So of the RAM and rigid or log rigid cohomology along 1 minus phi. I mean, that's all you need to know. I mean, I'm not even going to give, I mean, a more precise definition. What I want to say though, we will also use a variant called FP cohomology. So where FP stands for finite polynomial, and that was invented by Besser, where we replace 1 minus phi by Q of phi, where Q of t is a polynomial with coefficients in QP with constant term 1. Okay. So the starting point is as follows. So this follows from work of Nekova and Nisiol and Ertel Yamada. Namely that there exists a Syntomic regulator map which I will write R syn, so which goes from the H2 motivic of YH delta with coefficients in W dual twist 2 to the H2 syntomic of YH delta. Right, so in here, we had this motivic Eisenstein class, depending on the parameters T1 and T2. And I will write for the image Is T1, T2 syntomic. Right, so we have brought the Eisenstein class into the syntomic world. Now, what about the class arising from eta? Well, it turns out that from the definition of FP cohomology, there exists a surjection. So from the H3 FP of xg Klingen, V of 1 plus Q with respect to the polynomial p of t. So onto the H3 de Rham of xg Klingen with coefficients in V twist 1 plus q. And this is the part which is annihilated by p of phi. Now in here we have this class eta de Rham q, and it turns out that there exists a unique lift to FP cohomology, so which maps to this class. So, and this is unique if it is in the pi f eigenspace. In the pi f eigenspace. Right, now we have the following proposition. So namely that this pairing we want to evaluate so that this is the same as taking the Syntomic Eisenstein class and we pair it against the pullback of eta fp q. So, and here this is a pairing in FP cohomology. So up to here, nothing new has happened. I mean, this is the same approach. I mean, that Henri and Massimo and Victor used in the evaluation of the Syntomic regulator of the Balance and Flach class. Right, so the problem with this here is that we have no explicit description of the classes because there exists no explicit lift of Frobenius. Okay, so the problem, so there is no explicit lift of Frobenius, which means we can't describe these classes and hence the pairing explicitly. So what we want to do is to restrict to a locus where we have an explicit lifting of phi, namely the ordinary locus. So the idea is to restrict to the ordinary locus. So we use for this the following result of Ertel and Yamada. Namely that there exists an extension by zero map from the H3FP with compact support of xg Klingen greater or equal to 1 with coefficients in our sheaf. So to the H3 of xg Klingen. And one can show that this extension by zero map is an isomorphism on the pi f eigenspace. So this map is an isomorphism on the pi f eigenspace. Right, so how do we prove this? Well, the idea is, I mean, so the kernel and co-kernel of this extension by zero map are described by the FP cohomology of the x equal to 0 locus. Okay, so, and there is something which we call the Eigenspace Vanishing conjecture, which is forthcoming work of Kai Van Lan and Chris Skinner, which says that pi f does not appear in the FP rigid cohomology of the x equal to 0 stratum. So this is the Eigenspace Vanishing conjecture. So which will be proved by Lan and Skinner. Right. Well, okay. So this means that we can lift our class. So there exists a lift of our class eta fpq to a class which I will call eta fpq greater or equal to 1. So in the H3 fp with compact support of xg Klingen greater or equal to 1. Okay. So, I mean, this object, the greater or equal to 1 locus, appeared yesterday in David's talk. But so far, we have used no higher Hida theory. I mean, this link is going to be made later. Now we recall that if we intersect YH delta with the pullback of the greater or equal to 1 locus, that this is just the ordinary locus on YH delta. So this means that our pairing, say of Is T1, T2, so with the pullback of eta fp, so that this here is the same as restricting the Eisenstein class to the ordinary locus. So I will write this here as syn odd. So this here means restriction to YH delta odd. So, and we pair this here against the pullback of this class eta greater or equal to 1. But it turns out that even more is true, namely this here factor through the restriction to the ordinary locus on YG Klingen. So this here is the same as pairing this Eisenstein class so to the pullback of the restriction, well, I write this here as eta odd fpq. So this here is the restriction to xg Klingen odd. Right. So this looks good, right? Because we are now over the ordinary locus where we have an explicit lifting of Frobenius. But let me just make a comment about this object here, because something very strange is going on. So a remark about this element eta odd. Right, so remember what the special fiber of X Klingen looks like. So I'll draw it as this. So it divides here into 3 regions. Namely, this here is the ordinary locus. So where the multiplicative rank is equal to 2. There is the x equal to 1 locus, and there is the x equal to 0 locus. Now this class eta fp greater or equal to 1 has compact support towards the x equal to 0 stratum. So where is my colored pen? So this is this boundary here. Yeah. So what happens now if we restrict? So the eta odd. So this has compact support towards x equal to 0, so just that inherits it, I mean, because it's a restriction of this element over the greater or equal to 1 locus, but it, can I move the, oh yeah, right, okay, thanks. But it has no compact support towards x equal to 1. So towards this boundary here. Okay, so we have seen something like that before, namely in the talks of Boxer and Piloni. So this here is a rigid or finite polynomial analog, so of Boxer Piloni. So because they developed this theory, so of coherent cohomology, so with compact support so towards some strata of the special fiber, but not towards others. So, I mean, we discovered that independently of Boxer and Piloni, and we were rather amused. I mean, when we told Vincent about our discovery, and he then told us that he had made the same discovery turning up, I mean, in the theory. Okay, so we now write that this element, eta odd, is an element of the H3 FP-C0. So C0 means that it has compact support towards the x equal to 0 stratum. So of xg Klingen odd, so with values in our sheaf and with respect to this polynomial p. Right, so what have we done? So we have reduced the pairing to a computation so on xh delta odd. So this is good. So the next problem now is to relate it to coherent cohomology. So this is the next section. So the descent to coherent cohomology. Right, so the whole starting point is the following proposition, which is due to Banai and Kings. Namely, if we look at the restriction of the GL2 Eisenstein class, so here I is 1 or 2. So if we look at the restriction of the Syntomic Eisenstein class to the ordinary locus, then this has a unique description so in terms of a pair of global sections, so these are global sections, so on, well, the tube of the ordinary locus of the GL2 Shimura variety, well, with gamma 0 of p level structure, but I mean, gamma 1 of p level structure, but I mean, never mind. So in these global sections, they satisfy So they satisfy that nabla of x is equal to 1 minus phi of y, and nabla of y is equal to 0. Okay, so, and if you know about Syntomic homology, then these relations are precisely the analog of the relations which turn up in the definition of the Syntomic complex. So, I mean, we choose our Eisenstein class so such that the pair x and y so correspond to an Eisenstein class of weight minus Ti, which is p depleted, and a class of weight Ti plus 2, which is critical slope. Okay. So you will note that these are non-classical specializations of families of p-adic Eisenstein series. And they are precisely the ones which turn up in the construction of the p-adic L function. Yeah, so I mean, this shows that this here is a good starting point. I want to make a remark here. I mean, this here is critical slope. So it is p-adically cuspidal. And this has to do with issues of the cuspidal boundary. And I will come back to that in, I will hint later, I mean, why we make this choice. So this here is p-adically cuspidal. Okay, so we can represent each individual Eisenstein class as a pair of global sections, and we can then just use the formalism of cup product in FP cohomology to represent our exterior cup product, namely the I's, so T1 and T2. So this is again represented by a pair of global sections, which I will call alpha 2 and alpha 1. So these here are global sections. So over XH delta odd. So which again satisfies these relations. So nabla of alpha 1 is equal to 1 minus phi alpha 2. Nabla alpha 2 is equal to 0. And explicitly, alpha 2 is ET1 plus 2, P depleted, cup ET2 plus 2, P depleted. And the alpha 1 is a sum of the exterior cup product of P depleted and critical slope. So Eisenstein series. Well, and the terms in this series are decorated by varying powers of the Frobenius, but I'm not going to give the precise formula for that. I mean, that just comes out of the formalism of cup product in FP cohomology. Right, so we have now an explicit description of our Eisenstein class over the ordinary locus in terms of coherent cohomology. So what about the class coming from eta? What about eta FPQ odd? So we need an analog of, for this class, an analog of the result by Banai and Kings. And we do this via a new spectral sequence. So we recall that we have the BGG complex for V, so which is given, so let me write it as N0 to N1 to N2 to N3. So with differentials nabla 0, nabla 1, and nabla 2. So, and this here has a natural filtration, so which will give the BGG complex for V twist N. So I now define two complexes. So the first complex, so C bullet J, C0, so of xg Klingen odd with coefficients in V, is just a complex of the coherent cohomology in degree J with C0 compact support of xg Klingen odd acting on n bullet, this where the differentials are just the differentials from the BGG complex. Okay, I can certainly do that. And then I define C bullet J of an FP version of this, xg Klingen, so of V twist n with respect to a polynomial P. So this is defined as the mapping fiber, of C bullet J C0 of xg Klingen odd with values in V twist n. So here I just use the nth filtration step, of the BGG complex. And I take the mapping fiber along this polynomial P of phi. So this here is a coherent version of FP cohomology. Okay, so one can say what that is explicitly. So if we look at the Cij FP C0, so then this here is just the direct sum of the fill n of ni, direct sum the Hj C0 of x odd ni minus 1, and the differentials so they are given by a pair xy is sent to nabla of x and p of phi x minus nabla of y. So it really is extremely explicit. And we see here that this is very similar to the relations of Banach kings when p of phi is just a polynomial 1 minus phi. So now that we have this coherent version of FP cohomology, we need to relate it to the FP cohomology of the ordinary locus. And we have the following proposition. So, namely, there exists a spectral sequence which we call the Poznan spectral sequence. So, which is as follows. So the E1 term at Ij is just Cij FPC0. So, and this converges towards Hi plus J FPC0 of the ordinary locus of xg Klingen of V twist n with respect to the polynomial P. And this degenerates at the E3 page. So one should think of this spectral sequence as a finite polynomial analog of the Hodge to de Rham spectral sequence. So of the Hodge to de Rham spectral sequence. And the result of Banach-King's is just one application of a special case of this spectral sequence. Right, so now what can we do with that? So we have the following application. So we recall that we have this class eta defined in David's talk, which lives in the H2 of xg Klingen with values in the N1 term of the BGG complex. And it follows from Piloni's results that this gives rise to a class eta greater or equal to 1, which lives in the H2 with compact support of the xg Klingen greater or equal to 1 with values in N1. And we can then restrict this to the ordinary locus to get a class eta odd, which lives in the H2 C0 of xg Klingen odd with values in N1. And we now have the following proposition. And the proof of this proposition is very difficult. So, namely, that this class eta fp q odd, so our class in the fp cohomology, is uniquely represented so by a pair of classes in the coherent cohomology, namely this eta odd coming from Piloni's theory, and an element zeta. So this here lives, so the first one just lives, as I wrote, I mean, in the H2C0. So and the second term lives in the H2 with values in N0, and they satisfy that P of phi eta odd is equal, I should say here that the zeta is just unique if you take it in the pi f eigenspace. I mean, otherwise, I mean, there are some non-uniqueness issues. So P of phi eta odd is equal to nabla of zeta, and of course, nabla of eta odd is equal to 0. Okay, so this here is an analog of the result of Banach-King's describing this class in the FP cohomology in terms of classes in coherent cohomology. So let me just make one remark, namely about issues with the cuspidal boundary. So this result is only true if we forget so that eta is cuspidal. Because we need certain results on the degeneration of the Poznan spectral sequence, and this is only true if we do not assume any compact support towards the cuspidal boundary. Okay, so and this is the reason why we choose our Eisenstein class to be p-adically cuspidal for the pairing to make sense. So hence, so the Eisenstein classes are chosen to be p-adically cuspidal. Right, so that was the first remark. And the second remark, so there are many ingredients that go into the proof of this proposition, but in particular, this uses again, so the proof uses again the eigenspace vanishing conjecture. Eigenspace vanishing conjecture. So for the x equal to 1 locus, and then it turns out that this is much deeper, I mean, than the x equal to 0 locus. Right, so now that we have made the link with Piloni's theory and coherent cohomology, what can we do with it? So it follows that this pairing that we want to compute so we wanted to evaluate the pairing against the pullback along iota delta of this class eta fpq odd. So we can express that now as a cup product pairing in coherent FP cohomology. Namely, it's a pairing of this pair alpha 2, alpha 1. So with the pullback of this pair eta odd and the class zeta. Right. Now, one can expand this, I mean, using Besser's formalism of cup products in FP cohomology, and one gets a huge mess of terms. And then by a miracle, so it turns out that all but one of these terms are equal to 0. And the one term that we are left with is the following, namely, it is a pairing of theta to the R1 minus R2 of ice minus T1 depleted. So cup ice T2 plus 2 critical. So paired against the pullback of the class eta odd. And you will recognize that this here is precisely the value of the p-adic L function that David constructed at the value -1 minus R2 plus Q. Okay, so there we go. So let me make a few remarks here. So the first one is that the miracle so uses a very mysterious Hecke operator identity. A mysterious Hecke operator identity. So, well, David discouraged me from writing down this identity, but given that I have a few minutes, I am going to write it down. Namely, so it is as follows. So if we apply the product of the UP operators, say for on H, we compose this with the pullback of iota, and we compose this with the transpose Klingen UP operator. Then this is the same as the pullback along iota, composed with P times the diamond operator at P, composed with a Hecke operator Z prime, where Z prime is the Hecke operator, which at Iwahori level is given by the matrix 1P, 1P. Yeah, and I mean UP, U Klingen prime corresponds to the matrix 1P, P, P squared. So, I mean, we don't really have any conceptual explanation for that identity, but it is true. So the second comment is that the same strategy of evaluating a motivic cohomology class under the Syntomic regulator works when we replace one or both of the Eisenstein classes by GL2 cusp forms. So when we replace one or both, so Eisenstein classes by GL2 cusp forms. So this has applications to the GSP4 times GL2 Euler system. In the case when we replace one of the Eisenstein classes by a cusp form, so and the GSP4 times GL2 times GL2 cycle class. So that David mentioned yesterday. And I mean, we write down the details of this computation, I mean, in a recent preprint, which we put on the archive last week, but it is fundamentally totally the same. Yeah. And then I want to let me end by making a final comment. So David said yesterday, I mean, that the construction of the p-adic function using higher Hida and Coleman theory should generalize, I mean, to the settings of the other Euler systems that we have constructed. And the same is true for the strategy of the evaluation under the Syntomic regulator. So it should generalize to other Euler systems. So for example, so the Assay Euler system attached to a quadratic Hilbert modular form. So this is work in progress by Giada Grossi. So then Andrew Graham has constructed an infinite family of anticyclotomic cycle type Euler systems for U2N. With Wacker, sorry, Wacker, I mean, sorry, yes. So for U2N, so this is work in progress, so in progress of Wacker, Shah and Andy Graham. And it should apply to the U2-1 Euler system. So that was joint work with Chris Skinner. So this is a future project. So with David, Loeffler, and Skinner. Okay, so let me just sort of end by summarizing what we have done. So we have our Euler system. We have taken the bottom class of this Euler system and we have evaluated under the Syntomic regulator. And under pairing it against suitable elements arising from this coherent class eta, we obtain non-critical values of the p-adic function. So in David's talk, he will explain how to deform to critical values and then obtain some arithmetic applications, I mean, to the Bloch Kato conjecture and the Iwasawa-Meng conjecture, but finally also to an Eichler-Shimura isomorphism. But I mean, I leave that as a surprise in David's talk. Thank you very much.
Okay, so let's thank Sarah. Okay, so in talk, miracles and mysteries have appeared. Okay, are there questions for Sarah?
Could I make a remark, actually?
Oh, David.
I just wanted to say that these several different families of cohomology classes for GSP4 and GSP4 times GL2 and GSP4 times GL2 times GL2, they can be seen as a trilogy of Euler systems. So Henri and his co-authors had this lovely paper, Euler systems and p-adic functions, a tale in two trilogies. And here's a third trilogy.
Yeah, okay. So are there any other questions or comments? Thanks, David.
Maybe I can follow up on that comment of David. I mean, so now there are three trilogies, but if you continue this story and you looked at higher orthogonal groups, so something like 05 cross 06 or so, then this structure of a trilogy breaks down, right? You don't have any more this kind. It's not a systematic.
Yes, yes. I mean, I don't think that this is true in general. No.
Yeah, have people looked at these higher situations like 05 cross 06 at all?
Well, I mean, there is some work of Christophe Cornu, right?
Okay.
So, but I do not know. I mean, well, in this case, I mean, firstly, one doesn't know yet an explicit reciprocity law, but I also do not know. I mean, whether he has tried to develop, I mean, some general theory. I mean, how these Euler systems should be related.
There's also work in preparation, but on the UN times UN plus 1 case by I believe Jetchev, Skinner, and Wan, some set of people.
Yes, that is true.
The unitary diagonal cycle.
Mm-hmm.
Now, also, Sarah, can I ask you maybe to these last 3 examples that you pointed out, this example of Giada and so on.
Yes.
How do they exactly fit in with this GSP4 story? Is it like particular?
Well, they don't. Well, I mean, in a way, I mean, they're independent, I mean, of the GSP4 story, but the same methods, I mean, should apply. I mean, the construction, I mean, Giada is currently working on the construction of the p-adic function, I mean, for the Assay Euler system.
But so,
and I mean, the whole sort of theory of this partial compact support restricting to the ordinary locus and the Poznan spectral sequence and so on, all of this should work in general. So, yeah.
And how does this approach to the Assay compare with the approach of Yifeng Liu?
Giada, I'm sure you're in the audience, so that should be a question for you.
I am, yes.
Hi, Giada.
Well, maybe you can discuss it later with Henri, but that's a question for Giada.
So the first point, I think, like, I also need to develop some higher Hida theory for the Hilbert situation. So that's what I'm doing now, and like I will do the construction of the p-adic function. I'm not sure I understand what work you're referring to.
So it's still, this is still like an 022 cross 021 kind of weather system. But I mean, well, there was this work of Yifeng Liu where he considered this kind of thing via diagonal cycles, I guess. But you're looking.
But I mean, there he should get into a different region, right? I mean, I don't think that should compare directly, I mean, to our Euler system.
I guess the point is, if you start with the diagonal cycle, you have to be in a sign -1 situation.
Yeah, even.
And you can change to a sign +1 situation either by deforming in a p-adic family, which is the kind of stuff that Giada is talking about, or by using a congruence at some auxiliary prime to fix the sign, and that's what Yifeng does. Okay, with independent approaches, but starting from the same cohomology classes.
We said, I mean, that with these congruences, I mean, you can't deform, I mean, in cyclotomic families. So,
but so these ideas that you've explained today are even relevant for the kind of smaller rank situations of.
Absolutely. I mean, absolutely. I mean, the problem with the Assay case is, I mean, in some sense, the construction of the Euler system is totally parallel to the construction of the Balance and Flach Euler systems. But you can't construct a p-adic function that easily, precisely, because, I mean, in the Rankin-Selberg case, you really use that you can take the differential on GL2 times GL2 apart, right? So, and in the Assay case, you can't do this. So you really need the higher Hida theory and this partial compact support. And this is what Giada is currently thinking about.
Yeah, because indeed the pairing has the class in the H1 of the Hilbert modular surface and the
thanks. And the H1 does not break up, I mean, as a sum, I mean, of the H0 and the H1, like in the Balance and Flach case. So it was really frustrating that for many years, I mean, we couldn't do anything, even though in some sense, I mean, these two situations are extremely similar.
Somehow you can state very precisely the set of cases in which you don't need higher Hida theory. And you can get away without higher Hida theory if and only if you're working on a Shimura variety that's a product of 2 factors whose dimension differs by at most 1.
Yeah, precisely, because then you are precisely.
Yeah, because then you can get a middle degree class by taking the product of a holomorphic thing on one factor and an anti-holomorphic on the other.
Yeah, precisely.
And if you don't have that structure, you need higher Hida theory.
Yeah. Fantastic. It's interesting. That's sort of like the setting of Gangros Prasad in some sense.
Well, if I can say something, because there is a lot of projects mentioned I have a project with Basker about doing triple products, non-split triple products with similar methods. So
using higher Hida theory.
well, yeah, I think it will be necessary because we did the computation. It ends in the wrong degree. Yeah.
Yeah, sure. I mean, then I can believe that this strategy will work. Yeah.
So this is somehow very similar to what Giada was doing, but with the Eisenstein series replaced by an auxiliary cusp.
Yeah, indeed.
Yeah. So the size is like a non-split, yeah, GL2 and GL2 cross GL2, and like the triple product can be either a cubic field or like a quadratic times a split. I mean, there are like two cases, but yeah, we were thinking about the cubic thing. Yeah. Anyway.
Okay. Any more comments or questions?
I have a very painful question
Okay.
for
Who
Sarah.
has a painful question?
Me.
Oh, yeah. Okay.
So it seems that you crucially use this Eigenspace vanishing conjecture in your
Correct.
calculation. Could you say 2 words about it? Because
Well, what? Okay, right. So what you need? Okay, so the Eigenspace. So the Eigenspace vanishing conjecture. So that says that if we look at, so that pi f does not appear so in the rigid cohomology, so of x equal to 0 and x equal to 1. So, I mean, this you need, I mean, in order to uniquely, well, with some compact support condition, yeah. So, I mean, this is what you need. I mean, in order to lift your class to a class with compact support, I mean, over the ordinary locus. So, yeah, I mean, in the case of GL2, I mean, one can do this very explicitly. But I mean, and we use, or only actually uses that, I mean, in the Syntomic regulator calculation for the Balens and Flach case. But I mean, in general, I mean, this is rather difficult, but Kai Wen and Chris, I mean, have found a way, I mean, to prove that in quite great generality.
And does somehow depend on the ordinarity of pi f?
No, I don't think so.
Okay.
I don't think so.
Okay, thank you.
Well, as a bit of a follow-up to what Antonio asked, is there anything like an understanding of what the cohomology of this ordinary locus that you focused on looks like as a Hecke module? What automorphic representations arise?
Well, I mean, I guess, I mean, that's part of the.
I mean, you're using
the rigid cohomology. I don't know. I actually don't know.
Because what you're saying here is that certain automorphic representations.
I guess one should be able to deduce. I mean, from the Eigenspace vanishing conjecture. I mean, you can compare it with the rigid cohomology of the whole Shimura variety. So yes, I mean, you should know, I mean, what it looks like indeed.
So it's a piece of this cohomology somehow. That's the idea, right?
Yes.
And
we have, I mean, we write down, I mean, some quite precise consequences, I mean, of assuming this conjecture. I mean, for what that means for the pi f eigenspace in the cohomology of the ordinary locus. Yeah.
But is this vanishing conjecture kind of like a special case or some more general thing where you sort of characterize completely all the automorphic representations that arise in that particular part of the cohomology?
I believe so. I mean, I believe that is, I mean, that's what Chris said, right? I mean, that one can characterize what appears, I mean, in the strata.
Yeah, it's closely bound up with the Cariani-Schulze
yes, indeed, and that is used in the proof actually.
So what they prove is that for the L-adic cohomology, the L-adic cohomology of the p-adic model, you have somehow each automorphic representation contributes to one specific stratum in one specific degree. And you can compute which one it is in each case. And what we need to do for this vanishing conjecture is somehow translate that result from L-adic et al. To p-adic rigid cohomology. But the results is or at least expected to be the same.
Oh, that's where the conjecture is coming from this result.
Yeah. Indeed, yes.
All right. So let's thank Sarah and take a little break.